Our next section is entitled Solutions, which you may think, oh, here are all the answers to everything, life, the universe, everything within this section. Not quite. Solutions actually has a different definition. A solution is a homogeneous mixture that contains very small particles. Right? Homogeneous meaning the same throughout. So think of like salt water, right? So it's transparent and it contains tiny little sodium and chloride ions, but it looks the same throughout. You can't see where the salt is. Now colloids are related to this. They're also homogeneous mixtures, but they contain larger particles. Usually they're opaque. Examples would be fog, right? Fog is a colloid. It scatters light. If you are driving through thick fog, the worst thing you can do is turn on your high beams because it ends up scattering light and then it makes it even harder to see. Another example of a colloid would be jello. Right, jello, you can tell it's a colloid because if you take a laser pointer, you can shine it through and you can actually see the beam. You can feel like Luke Skywalker, waving your your laser beam through your jello salad. Now, solutions actually contain two different things, right? The solvent, which is whatever you have the most of, and the solute is whatever you have less of. Now, also the solvent is what keeps its state. So for instance, if you have water and you dissolve some sugar in it, water would be the solvent because it's a liquid and it remains a liquid. The sugar would be the solute because it goes from a solid and takes on kind of a liquid form as it dissolves into the water. So the solute would be sugar, the solvent would be water. Now, there are cases in which you can have multiple solutes. Right? If you have something like coffee, it has caffeine and tannic acids and some sugar and a whole bunch of different things dissolved in the solvent, which would again be water. All right, so you can have more than one solute, but typically only one solvent. And then you can also have aqueous solutions, which are the most common. This is where the solvent is actually water. Now, solutions can be any two phases mixed together. We can have gaseous solutions where a gas is dissolved in a gas. For instance, air. The solvent in air would be nitrogen. There's oxygen and carbon dioxide and water vapor and some other things dissolved in that solvent. So you can have multiple solutes. You can have a liquid solution, in which case you could have a gas dissolved in a liquid like soda, carbon dioxide dissolved in your water. You can have liquid dissolved in liquid like beer, in which case you have ethanol, which is drinking alcohol, dissolved in your water. And you can also have a solid dissolved in a liquid, as in the case of seawater, where you have sodium chloride, which is a solid dissolved in your liquid water. You can even have some kind of weird things like alloys, which are a solid dissolved in a solid, for instance, brass or 14-karat gold. Right? You have multiple things that are all solids, but they're mixed together. They're dissolved into whatever your solvent is. And then the strangest of all, I think, are the amalgams, which is where you actually have a liquid dissolved in a solid. An example of this would be silver fillings. If you're like me and you didn't take good care of your teeth when you were a kid, you have a bunch of silver fillings, which is actually mercury and lead dissolved in some silver, and then they pack that into your teeth. So those would be known as amalgams. Now, when it comes to solubility or dissolving things, we need to remember the chemist's rule of thumb that like dissolves like, which means that polar molecules dissolve nicely in other polar molecules. Nonpolar molecules dissolve in nonpolar molecules, but nonpolar and polar don't mix. That's like oil and water, literally, where one is polar and the other is nonpolar, and so the nonpolar vegetable oil separates out from the polar water. Now, gases are always soluble in each other, right? If I have, air, I can introduce some extra carbon dioxide into that air by exhaling, and the carbon dioxide mixes in nicely and it dissolves in there. Now, liquids aren't always soluble in each other. When they are soluble, we say that they are miscible. So for instance, alcohol and water, you can mix them in any proportion and they're completely miscible. Whereas oil and water are immiscible, or gasoline and water are immiscible because they don't dissolve in each other. Now, sometimes you can mix any ratio, like in the case of water and alcohol. You could have 99% water and 1% alcohol, or 99% alcohol and 1% water, and it still mixes easily. However, most things have a solubility limit, where there's some maximum amount of solute that you can dissolve. So for instance, if I took a glass of water and I started to dump some salt into it, at some point I would kind of max out the solubility, right? The salt would no longer be soluble because the water simply just cannot hold any more salt, in which case the salt would just start to accumulate at the bottom of the glass. We can actually have different types of solutions, and I actually just described one of these. So in the case of having a glass of water, right? Or actually, here's something that my brother and I used to do, which is such a bad idea, which is why we have such horrible teeth. Is that we'd take a glass of water and we would actually dissolve in some sugar into that water. All right, so I'm going to go ahead and dissolve in some sugar here, and the sugar dissolves very nicely in water. Okay, and at some point you've maxed out the solubility, right? The sugar just cannot dissolve anymore. The water just can't hold anymore, and so you start to get like a pile of sugar stacking at the bottom. Now, my brother and I would actually keep stacking it up until you have just this slushy of like sugar, which is again really bad idea. Now, at this point, when the water cannot hold any more sugar, we call that a saturated solution. It's where we've maxed it out. It just cannot hold any more solute at that temperature. Now, up to that point, we had an unsaturated solution, which means it could still hold more sugar. So you start out, it's unsaturated, it can hold more, it can hold more, it can hold more, but at some point it's reached the saturated state, in which case any extra sugar that you dump in just stacks up at the bottom. Now, you can actually make something called a supersaturated solution, which is a little tricky, but this is how you make rock candy. I don't know if you've ever tried making rock candy, but it's a lot of fun as long as you're patient. But the idea is you do exactly what I just described, dissolving a bunch of sugar in water, but then you actually heat up the water itself. So you put this on a burner or whatever, and you start to heat it. And as you heat it, you'll see that the sugar will actually dissolve. Okay? And so you can keep adding more and more sugar into there because you've increased the temperature. And by increasing the temperature, you have now made the sugar more soluble, or you've increased the solubility threshold, or the limit for the sugar. So you keep going, and then what you're going to do next is you're going to shut off the flame, and you take this and you can let it slowly cool. All right, you don't want this to cool very quickly, because at this point you have something known as a supersaturated solution, where you actually have tricked the solution into containing too much solute, more solute than it should be able to handle, and this is very unstable, which means that if you go ahead and put something in here that will allow the sugar to start crystallizing. So for instance, what I usually do is I would actually take like just a pencil, and you'd put the pencil all the way across, and then you would dangle a little string from that pencil, and then you'd weight it with like a little paper clip or something. And by doing that, you've allowed the sugar to start to crystallize onto something, onto the paper clip and the string, and so you'd actually see these little sugar crystals start to form as the sugar starts to precipitate out of the solution. After a couple weeks, it's ready to go. You can go ahead and pull out the string and eat the delicious rock candy. Nowadays, I'm far too lazy. I just go down to the store, the candy store, pick them up for like 75 cents or whatever, and they're delicious. But that's what we call a supersaturated solution. One of my favorite examples of supersaturated solutions is sodium acetate. So if you take sodium acetate and you dissolve it into water, and you make a supersaturated solution, just like I mentioned before, by heating it up and slowly cooling it down, you can actually make like these really cool little hand warmers. This one's heart-shaped, and it has been dyed red, because it's a heart and everything. But what happens is there's a little disc. You can see the little metal disc in there, and when you bend that disc, it has this rough surface inside, which when that is exposed, it allows the crystals to start forming. And so literally instantaneously you get these sodium acetate crystals that start forming. You can see how they kind of blossom out from that metal disc, and within about, I don't know, 10 seconds, the entire thing has crystallized out. And this happens to be an exothermic reaction or exothermic process, and so it produces heat. And so this is a nice little hand warmer, keeps your hands warm. And then you can actually reverse this by sticking the little hand warmer into boiling water, heating it up. That dissolves the sodium acetate back into solution, and then you can repeat the entire process. There are actually some really fun videos on YouTube that you can check out. Just look for hot ice, I think is one of the terms, even though it's not ice, and it always bugs me when they say that, or supersaturated sodium acetate solution. You can see how you can actually build sandcastles and so forth out of this stuff. Very, very fun. Now, a couple of trends that you should be aware of when we are discussing solubility. One thing is that temperature definitely affects solubility, but the trends are actually reversed depending on whether you're talking about a solid dissolved in a liquid or a gas dissolved in a liquid. For solids, higher temperature means higher solubility. So you know this because you know that sugar dissolves more quickly and easily in hot coffee than it does in iced coffee, right? Because as you increase the temperature, you make the solids more soluble in the water. But for gases, it's the opposite trend. As you increase the temperature, you're actually decreasing the solubility of the gases in the water. You actually have experience with this as well, because if I asked you, you take 2 glasses of soda, you put one in the fridge, you put one in the sun, which one's going to go flat faster? And you'd say, well, the one in the sun goes flat faster because as the sunlight warms up the liquid, the gas will start to foam out of it or start to bubble out of it, and then you have flat soda, which no one likes. So you definitely want to keep your soda in the fridge if you want to keep it nice and fizzy, once you've opened it, of course. Now, the other trend that we need to worry about is pressure, right? So it turns out that this only applies to gases dissolved in a liquid, like Coca-Cola or whatever, but higher pressure means higher solubility, which is why at the Coca-Cola bottling facility, when they package these things, they pump in massive amounts of carbon dioxide inside that can. So it's under very high pressure. And as soon as you open it, you pop the top and you hear the little hiss. That's because the gas is escaping. And as you decrease the pressure, now it starts to bubble out. And so if you want to keep your soda fizzy longer, you need to do 2 things. You should always, A, make sure that you keep it cold, and B, make sure that you increase the pressure as much as possible. In fact, I've seen these on infomercials, these little bottle cap things that you screw on there, and it has a little pump on it, and you can pump up the pressure, and it should actually work if you increase the pressure enough, because you're making the carbon dioxide more soluble in the liquid. I just have a hard time spending 10 or 20 bucks on this little soda topper thing if for a 99 bottle of soda. That it just doesn't seem to make a lot of sense to me. But anyway, it's one of the few things that's on TV that actually is real. Now, I believe I mentioned this before, but electrolytes, we can't really talk about solutions without talking about electrolytes. Electrolytes are just substances that when they're dissolved in water, they conduct electricity, or the resulting solution conducts electricity. This is because of the ions. Right? So ionic compounds like sodium chloride, table salt, as soon as you put that in water, the water can now conduct electricity, or the solution can conduct electricity because of those moving ions. Now, there are different levels of electrolytes. Some are strong electrolytes, in which case you put in 100 molecules, all 100% dissociate into ions. You can also have weak electrolytes, where maybe you put in 100 molecules, but you only get 2 or 3 or 5 of those molecules actually splitting up into ions. And then you can have non-electrolytes. This would be like sugar, in which case you put sugar in there into water and it dissolves nicely, but there are no ions because it's a molecular compound. So even though it dissolves, it doesn't dissociate into ions, and therefore you do not have an electrolyte solution, and it won't conduct electricity at all. Now, in order to discuss concentration or solutions, we need to discuss concentration, and we need to have some units for this. So there are a couple of different units that we could deal with. The first is mass percent. So for mass percent, it's a very simple formula. You take the mass of your solute, divide by the mass of your solution, multiply it by 100 to make it into a percent. So, relatively simple, right? Now, The only tricky part is here, you'll notice in the denominator there we have mass of the solution. Remember that the solution is the overall, beaker full of stuff that you have. That contains the mass of the solvent plus the mass of the solutes, right? And it could be more than one solute. So if I give you, if I say that you have something dissolved in 100 grams of solution, you just divide by 100 grams of solution. But if I say that you have 100 grams of solvent and 30 grams of solute, then you need to make sure that you get the overall solution, which would be 100 plus the 30 grams. And then you can plug that into the denominator. So let me go ahead and give you an example here. This is an easy one. So here I have 35 grams of sodium chloride, and that is dissolved in 150 grams of solution. So notice that I give you the grams of solution, so I make this one really easy. So it's 35 grams of solute on top, 150 grams of solution on the bottom, and I just need to multiply that by 100. Notice that my units cancel out, so there are no units here, besides just, it's a mass percent. And let's see, 35 divided by 150 times 100. Looks like I have 2 sig figs because I have 2 and 2, so I can have 2 sig figs at the end of the day. So this is 23% by mass. Now there's also another one that's by volume. It would be the exact same thing, except you'd be using milliliters instead of grams, right? Or liters. It doesn't really matter as long as your units cancel out. Let's go ahead and try another one. This one's going to be a little trickier. So here I tell you that you have 18.5 grams of glucose. This is dissolved in 250 grams of water. Now, for this one, I know back up 1 second. Sorry about that. For this one, I know the mass of the solute, right? 18.5 grams. But what's the mass of my solution, which is what I need to put in the denominator? Well, it's not 250 because that's just the mass of the solvent, the water. So it's 250 grams of water plus the mass of the solute itself, the 18.5 grams of glucose. So remember that here on the bottom, this is the mass of the solution. Oh, there we go, solution. Okay, not just the solvent. All right, multiply this by 100 to make it into a percent, and plug it in. 18.5 divided by parentheses 250 plus 18.5, and then multiply that by 100. Looks like I have 2 sig figs, so I'm actually going to round that to 6.9% by mass, and that would be my answer. So not too bad, right? All you need to do is just follow the formula, make sure your units are the same so that you can see that they cancel out, right? You cannot have grams and kilograms. You'd have to convert them both to the same thing. Now, that's mass percent, right? What about ppm, or parts per million? So this is a common one that's used in things like water quality. So if you get your water tested, it'll tell you, oh, you have 3 parts per million arsenic in your water, and so forth. So this actually probably looks relatively familiar because you're taking the mass of the solute and dividing by the mass of the solution. And then you're multiplying, in this case, by 10 to the 6th. Why 10 to the 6th? Well, 10 to the 6th is 1 with 6 zeros after it. Oh, that's a million, right? Hence the name, parts per million. And so really all you're doing is you're doing mass percent, but you're multiplying by a million instead of multiplying by 100. In fact, percent, por ciento, means per 100, right? So you really could call mass percent, you could just call it pph for parts per 100, but no one ever actually calls it that. But parts per million, you multiply by a million. What about parts per billion, ppb? Well, parts per billion, you would just do the exact same formula, right? This whole thing, but multiply by 10 to the 9th because that's a billion. Parts per thousand, you'd multiply by 1,000 instead. Now, by far the most commonly used unit for concentration in chemistry would be molarity. So molarity, you probably see the word mole in there, and that's exactly what this is. This is moles of solute over liters of solution. So that's an important one that you should definitely remember, okay? So molarity is moles over liters, right, or moles per liter. Now this is abbreviated just capital M, so you might see something that's 5 molar. And what that means is you could actually translate that into meaning that you have 5 moles of your solute per liter of solution, right? So you could either write moles per liter or just write capital M for molarity. So let's go ahead and try calculating molarity. If I have 7.2 moles of lithium nitrate and I dissolve it in 935 milliliters of solution, what's the molarity? Well, to calculate molarity, remember that molarity is moles of solute over liters of solution. I have moles, that's already given. Ooh, I don't have liters, I actually have milliliters. So I could do a quick domino problem, but I know that 1,000 milliliters is 1,000 milliliters is 1 liter, so therefore I just divide this by 1,000, and this is equal to 0.935 liters. So now I have both my moles and my liters, so to calculate molarity I simply take 7.2 moles and divide that by 0.935 liters. And that's it, right? Simple. So 7.2 divided by 0.935. I have 2 sig figs, so I'm going to call this a 7.7, and I could either write moles per liter, or I could write 7.7 molar, capital M. Either one's correct. All right, so you'll typically see this, something like this written on bottles, but it really just means moles per liter, molar. Let's go ahead and try another one. In this case, I have 155 grams of calcium chloride, and that's dissolved in 2.5 liters of solution, and I want to know what's the molarity. This one's going to be a little trickier because notice on the last one, I was given moles, right? So I could simply plug that in. This one I'm not given moles. In fact, this one I am actually given grams, right? So before I can do anything, I need to take these grams here and I need to convert that into moles, right? Because remember that the formula for molarity is moles over liters. So let's do a quick domino problem. 155 grams, and I need to convert that into question mark moles. So hopefully you remember how to do molar mass domino here. Now, the next thing is this is calcium chloride. I know that calcium is a 2+ because it's in column 2A. Chloride is a 1-. So CaCl, I take the 2 and the 1 and I flip that, and that becomes a 1 and a 2. So the formula for calcium chloride is CaCl2. So I'm actually going to go onto my periodic table, and I'm looking up the molar mass of calcium, which is 40.08 grams. And then I have 2 chlorides. Each one is 35.45 grams. Add those up. So 40.08 plus 2 times 35.45. And it looks like my molar mass is 110.98 grams per mole. Or in other words, as I'm going to write up here, 1 mole is equal to 110.98 grams. All right, I just double check that my units cancel. Grams cancel grams, moles cancels moles. So I've set this up properly, and I'm just going to type in 155 divided by 110.98, and it looks like I have I'm going to go ahead and leave a few more sig figs here, even though I know I can't have them at the end, but 1.3966 moles. And what are my liters? Oh, it's already given to me. Nice. I didn't even have to convert it. It's already in liters, which is nice. If it was in milliliters or centiliters or something, I'd have to go ahead and convert that. But I'm just going to take my 1.3966 and divide by 2.5. Now, I only have 2 sig figs to work with because my 2.5 liters only has 2 sig figs. So I'm going to go ahead and round this to 0.56 molar, or moles per liter. And that would be my answer right there. So again, this takes a little more time, especially if I'm given grams and I need to convert that to moles. But really, it's just a simple formula, right? Moles per liter. You just plug it in and you're done. Now, for our next trick, we are going to, sorry, trying to make it sound like some amazing thing, but we're actually going to be using molarity as a conversion factor in this next problem. So this is kind of an interesting thing, but remember that molarity, for instance, if I say that something is, in this case, a 0.10 molar solution, that's the exact same thing as saying it's 0.10 moles per liter, or I can rewrite that and say that it's 0.10 moles is equal to 1 liter. Because if it's 0.10 moles per liter, that means if I have 1 liter of solution, it's going to contain 0.1 moles of stuff, right? So the nice thing about this is that this is a conversion factor, right? So I'm going to go ahead and try using that conversion factor to set up a nice little happy domino problem, hence the lovely yellow color here. All right, so the problem says how many grams, right? So question mark grams. And let's see, it says that I have 125 milliliters of solution. 125 milliliters. Now notice that I do have this other number over here, but that is my conversion factor. So I don't want to start with that. I want to go ahead and leave that alone until the end. So I'm going to go ahead and set up this domino here. And actually I'm going to erase that because I'm going to need a couple of dominoes. The first one is, notice that here this is in liters, right? So I need to convert this to liters. So 1,000 liters is equal, 1,000 milliliters is equal to 1 liter. Now that, if you'll notice, gets rid of my milliliters. But now I'm in liters, so I can go ahead and use this domino up here in the top right. I can go ahead and plug that in. And it tells me that for every 1 liter that I have, it contains 0.10 moles. Now, I double check, and it looks like my liters cancel out nicely. So if the problem asked for moles, I would be all set because I have moles. But the problem actually wants grams. So I need to go one more step, right? I need to figure out what's the molar mass. What is the mass of 1 mole of sodium hydrogen carbonate? Well, I'm not going to write this out, but on my periodic table I have sodium, which is 22.99, plus 1 hydrogen, which is 1.01, plus 1 carbon, which is 12.01, plus 3 oxygens, which is 3 times 16. And if I add that up, it says that it's 84.01 grams. So now I just go ahead and double check. Moles cancels moles, grams cancels grams. Everything cancels out nicely in this case, which means I know I've set it up properly and I've used this molarity as a conversion factor. Now it's just a matter of plug and chug, right? So it's 125 times 0.1 times 125 times 0.1 times 84.01. And just go ahead and plug that in real quick. And then on the bottom I just have 1,000, so I'm just going to divide that by 1,000. Now notice that in this problem it looks like I have 1, 2, 3 sig figs here. I have 2 sig figs over here, so my final answer can only have 2 sig figs. So this actually comes out to 1.1, and my units have to be grams. So what this means is that if I took 125 milliliters of this 0.1 molar baking soda solution, right, sodium bicarbonate solution or sodium hydrogen carbonate. If I take 125 mils of that, it'll actually contain about 1.1 grams of sodium bicarbonate. So this is where molarity comes in really handy, because you can actually do solution stoichiometry now. Not that I'm going to make you right now, but you could, because now that you can see how to convert from milliliters into liters, into moles, into grams, and back and forth, you can do all kinds of things. Now, if you're like me, you don't go and buy the pre-made orange juice because it's expensive, right? You probably get the little cans of orange juice concentrate. I love that stuff. Actually, I really love the frozen limeade concentrate. Pop open one of those on a hot day with a spoon and you just eat it straight out of the can. Oh, so good and so bad for you. But anyway, but what you're supposed to do is you take the juice concentrate, you dump it into a big pitcher, and you add water. And by adding water, you're diluting it. You're adding more solvent to decrease the concentration of your solute. Do the same thing if you mop your floors with Pine Sol, right? It's like a cap full of Pine Sol for every gallon of water or something. And so you're diluting it. Now, we actually have a formula for this, which is M1V1 equals M2V2. Or in other words, your initial molarity, or your initial concentration times your initial molarity times initial volume is equal to your final molarity times your final volume. And so we can actually use this in a set of problems. And this is a lot like the gas laws that we talked about. So just like in those cases, we don't really care what our units are as long as we're consistent. So let me show you what I mean. So in this case, it's talking about diluting things, right? So I know right off the bat that this is the only formula that I can use. M1V1 equals M2V2. Some books will actually put C1V1 equals C2V2 for concentration instead of molarity. It doesn't matter. Now, just like in the gas laws, I like to write out each of my variables here just so that I can fill them in. Alright, so in this case, let's see what we have. It says that we have 15 milliliters, so our initial volume is 15 milliliters, and it's of a 3.3 molar solution. And we're diluting this so that the final volume is now 4 liters. And I want to know what's the final concentration. So, it looks pretty straightforward. Notice, though, that I have molarity for my initial concentration, so my final concentration also has to be in molarity so that the units will cancel. All right, if they were in millimolar or picomolar or something, that's fine as long as we're consistent yet again. All right, now the next thing is, notice that here I have milliliters, here I have liters. That's not going to work. I need to go ahead and change one of those over. So I'm going to go ahead and just convert that one. So 4 liters is the same thing as 4.0 times 10 to the third milliliters, right? It's 4,000 milliliters. So now let's go ahead and just plug these things in. So M1 is 3.3. Oh, and notice that my units cancel, so I'm going to be lazy and just leave off my units. Oops, actually, it's not this one, it's this unit that cancels. Alright, so 3.3 molar and 15 milliliters. This is equal to M2, which I don't know, so I'll just leave that as M2, times 4,000, or 4 times 10 to the third. I'm writing in scientific notation just to show that I still have 2 sig figs. Not a big deal, but anyway. So to solve for M2, I'm just going to divide both sides by 4,000 here, or 4 times 10 to the third. Because it's algebra, I have to do the same thing to both sides. So that whole thing will cancel. And therefore, M2, my final concentration is 3.3 times 15 divided by 4,000. And it looks like I have 2 sig figs, so the answer comes out to be 0.012 molar. And that's going to be my final answer there. Now, I like to do a sanity check just to make sure that this makes sense. So notice that I have a 3.3 molar solution, and I'm increasing the volume from 15 milliliters to 4,000 milliliters. So I really cranked up the volume here. And notice that the concentration went from 3.3 all the way down to 0.012, which makes sense. By adding so much water, I'm going to dilute the solution quite a bit. So the concentration is going to go way down. So now we're actually done with the calculations, but I wanted to mention something kind of interesting, something known as colligative properties. So colligative properties are properties of a solution, but the value of these properties depends only on the number of dissolved particles, not the identity of those particles, which means all I care about is how many particles I have, not whether they're chloride ions or glucose molecules or lithium ions or whatever. All I care about is the sheer number of dissolved particles. Now there are three colligative properties we're going to be concerned with. These are boiling point elevation, freezing point depression, and osmotic pressure. So let's go ahead and look at each of those. The first thing is that with boiling and freezing points, it turns out that whenever you have a solution, let's say that you have water and you dissolve some sugar in it. Well, what happens when you dissolve the sugar in it? What happens to the freezing and the boiling points? Well, it turns out that you're actually going to raise the boiling point and you're going to lower the freezing point. So boiling point elevation, freezing point depression. Okay, so that means that your sugar water solution will boil at a higher temperature. Maybe instead of boiling at 100 degrees Celsius, maybe it boils at 101 degrees Celsius now. And instead of freezing at 0, maybe it freezes at -3 degrees Celsius now. And remember that all we care about is the number of particles. We do not care about what those particles are. As long as they dissolve in water, it's going to affect the freezing point and the boiling point. All right, so let me give you an example of this. When my mom, when I was young, my mom would be making spaghetti. She'd always dump in some salt into the pot of water. And I'd ask, well, why'd you do that? And she said, oh, it actually makes it boil faster. And I thought, okay, that's great, till I took my first chemistry class. And then I found out that by adding salt to the water, you're actually increasing the boiling point of the water. So it actually takes longer to boil, right? And so I went home and I told my mom this. And here's a little rule of thumb. When your mom's making your food, she's right. It doesn't matter whatever she's saying. Otherwise, she'll just throw this wooden spoon at you and say, fine, make your own spaghetti. So turns out that it'll raise the boiling point. This is why we put antifreeze into our car radiators, because it keeps them from boiling over in the summer and it keeps them from freezing in the winter. Because by adding that in, not only do you raise the boiling point, but you lower the freezing point. This is also why we put rock salt on the path when it freezes over in the winter, right? So you go out there and you throw some salt on there, and it's actually going to lower the freezing point. And so as long as the temperature is not too cold, it'll actually melt the snow and the ice. Now, let's say that your mother-in-law is coming over to visit in the winter, and your wife says, oh, you need to go and salt the path because you don't want her to slip on the ice and break another hip or something. And so you go out there and you realize, oh, I don't have any rock salt left. Dang it. Can you just go in and grab a salt shaker and just use a whole bunch of salt, like table salt? Sure, you could. And as long as you have enough, it would totally melt it. Now, what if you're out of table salt? Could you use sugar? Well, yeah, you could, because it dissolves in water. And so you could dump a bunch of sugar on there. And then when it would actually melt the ice. Plus, it would have the added benefit that with all that sugar water, if she does slip, she'll get coated in sugar water. And then the fire ants will come out. And then they'll rip the flesh from her bones. Anyway, enough about my mother-in-law. So, it turns out, though, that as long as it dissolves in water, it will lower the freezing point and raise the boiling point. What about sand? No, sand won't work. I mean, it grits the path and it gives you traction, but it will not melt the ice. All right. Also, if you add it to the water when you're cooking spaghetti, it will not raise the boiling point of the water, and it makes your spaghetti all gritty, so I don't recommend that. Okay. Now, one more thing that I do want to mention really quickly, because some people get confused on this. When I mention that I only care about the number of particles when I'm, looking at colligative properties, I really mean that I only care about the number of particles. But here's something else. If I'm using, let's say, glucose to melt the ice, when I put that, this solid glucose, I'm just going to erase that. All right, when I put solid glucose into water, it dissolves, but it doesn't split apart. It doesn't dissociate. So if I put in one of these, I get out. Actually, I'll change the color up here. All right, so if I put in one of these, it looks like I'm going to get out. So one of these turns into one of these over here. So I don't get a whole lot of stuff out of this. Now, what if I put in table salt? Okay, well, table salt, when it dissolves in water, splits apart into sodium and chloride ions, which means that if I put in 1 mole of this, or 1 molecule of this, I'll get out 2 moles or 2 molecules of this. So table salt will be better at dissolving the ice, but simply because it has 2 particles rather than 1 particle. All right. Now let's try one more. What if I use something like calcium chloride? So this is the fast melt stuff, the expensive stuff that you can buy. Well, this will split into calcium, and it will split into 2 chloride ions. So in this case, by putting in 1 of these, you're actually getting out 3 of these, 1 calcium and 2 chlorides. So you can see that calcium chloride would definitely work the best out of all of these, but simply because it has more particles. It doesn't matter that we have calcium ions versus glucose molecules. All right, I could use glucose, but I'd have to put in 3 times as much to achieve the same effect. All right, so now that we've discussed freezing point, depression, boiling point, elevation, what about osmotic pressure, this other colligative property? Well, in order to understand osmotic pressure, we need to know what osmosis is. Right? Well, osmosis is simply the passage of water and small molecules across a semi-permeable membrane. So, for instance, your cells are surrounded by a semi-permeable membrane, which allows water to go in and out and certain small molecules, but it keeps things like your DNA and proteins and so forth from just drifting out of your cells. All right, so the important thing to remember is that water will always move from an area of low solute concentration to high solute concentration. All right, so this is very important. And it seems kind of counterintuitive. The way I always think of it, though, is that the water is trying to equalize the concentration on both sides. So if it sees one side that has a whole bunch of molecules, and it doesn't matter whether these are glucose or salt ions or whatever, right? Because it's a colligative property. If it sees a side with a whole bunch of solute particles, the water will try to move across to dilute that out until the concentration is equalized on both sides of this. All right. Now, you could try to prevent the water from moving across by exerting a force. You could try to exert a force going in the opposite direction to try to force the water to stop, right? Now, that force that you would have to apply, that pressure that you'd have to apply to stop osmosis is called the osmotic pressure. And it makes sense that the greater this difference in concentration, the higher the osmotic pressure will be. What I mean is, if I have a ton of particles over here, right, a ton of these, then the water really, really, really wants to get across, right, to try to dilute this out, because one side is so much more concentrated than the other. So that would be a very high osmotic pressure. Whereas if I have a situation in which there's almost identical concentrations on both sides, then I have a very small concentration gradient, so the osmotic pressure would be much, much lower. So what does this have to do with us? Well, it turns out that osmosis is vitally important for us as humans, because we don't want water to either start flooding into our cells or to start abandoning ship and leaving our cells. So we want to be consuming or uptaking things that are isotonic, solutions with the same osmotic pressure as body fluids. Now, I don't expect you to memorize these numbers, but if you work in a hospital, you'll probably note that the IV solutions are typically a 0.92% saline solution or a 5% glucose solution, because those are isotonic to the body. Now, the great thing about this is that if I have an isotonic solution and I put one of my red blood cells into that solution, water can go in and water goes out because there's a semi-permeable membrane, but there's no reason for water to go one direction or the other. So a little bit comes out, a little bit goes in, but there's no net change in the shape of my red blood cell. Okay, so it still kind of looks like a happy little, flattened donut thingy, and everybody's happy. Now, what if I were to inject somebody with an IV solution that happens to be that happens to be hypotonic, which means that it has a lower osmotic pressure than my body fluids? Well, in that case, there are more solute particles. In fact, let me draw in a few of these. So if it's hypotonic, it means that I have a whole bunch of solute particles within the cell and not very many outside of the cell, right? And so what will happen is water will start to flood into my red blood cells, and the red blood cell will actually start to swell, and if the concentration gradient is large enough, it will actually burst open, and this is called hemolysis. And this is a really, really bad way to go, right? Because your cells literally start rupturing. This happened a while back. There was a radio contest called Hold Your Wee for a Wee, and there was a woman on there, and they were supposed to drink like gallons of water and then hold their urine as long as they could, and whoever would win, whoever held out the longest would win a wee. And one lady actually died from this. And so a bad idea to just chug massive amounts of water. Now, your body knows when you've had enough, so it's not a common thing that you just like, oh, I'm a little thirsty, and you drink a couple glasses of water and you keel over. It doesn't work that way. Usually you're either force-fed it, or you are, like sometimes soldiers in the desert will actually be dehydrated, and so when they get back, if the medic's not paying attention, they'll actually give them too much water, and the body is already whacked out from being dehydrated, and so it doesn't realize that it's uptaking far too much water, and then the person can actually die from having too much hypotonic solution being put in. Same thing would happen if you started to give people IVs full of just distilled water, right? It wouldn't work. You need to make sure that it's isotonic to the solution, or to the blood. Now, the next one would be hypertonic. Hypertonic means that there are, it's too salty or too many particles outside of the cell. Okay, so here I'm just adding a whole bunch of particles out here. So it's very, very salty or very concentrated solution outside the cell, and maybe only a few inside. And so what happens here is that water will start rushing out of the cell to get to the higher concentration of solute out here. And when that happens, the cell starts to shrivel up, it shrinks, and this is called crenation, and you can also die from this. This happens to a small extent when you drink a lot of soda, right? Because soda is very sugary, and so have you ever noticed that you actually feel thirstier after drinking a soda? Yeah, it's because it's actually kind of sucking out a little bit of the water out of your cells, and it's actually dehydrating you slightly. It's not enough that you really need to worry about it, but if you were, let's say that you go on a cruise ship, right? So you're on a cruise and you're attacked by pirates, right? Happens all the time, of course. So you're forced into a lifeboat and set adrift in the open sea. And you start to get really thirsty. Should you drink the water? Well, no, because the water is so salty that it would literally start ripping the water out of your cells and so forth, and you become dehydrated, you start getting nauseated and vomiting and horrible diarrhea and all these nasty things, you hallucinate, and then you die. So really the moral of the story here is make sure that you're only taking in isotonic things, but more importantly, if you are, let's say, given cruise tickets, you should just send them to me, because just for safety's sake, much safer that way, right? I'll take care of them. You don't need to worry about it. I always carry my own reverse osmosis filter just in case of pirate attacks. All right, so that's it for our study of solutions. I'll see you next time.